So this is perhaps my favorite lecture. Don't hold me to that. I might say that other lectures in the future are my favorite, but this is the one in which we take the expanding universe that we talked about last time and we ask, what does that really mean? We won't answer that question until the next lecture, but this question is going to take us into trying to understand how space and time work. And this is the real thing that made Einstein quite a famous international celebrity. He is the person who figured out how space and time work. And he figured out how they're related to gravity. So this is something in which Einstein did better than Isaac Newton did, which is a hard thing to do. So we're going to go from what Isaac Newton did up through Einstein, explaining along the way how we get there. And it really is a set of deep ideas about the structure of space and time that are counterintuitive. So we'll be thinking pretty hard about why things are like that and why they're one way rather than another. So let me start just by thinking about what the ideas of space and time are supposed to be. Space and time are what help you locate things. Space tells you where things are, and time tells you when things are. So let's think about space. To begin, scientists like to say that space is three-dimensional. What does that mean? That means that if you want to locate the position of an object, in principle, you need to give me three numbers. And the way that you can give me those three numbers can be different depending on the circumstances. So for example, the three numbers you give me might be the height of something, the length of something, and the breadth of something. Once you give me those three numbers, you've specified its dimensions entirely. If you only gave me two numbers, it wouldn't be enough. So we say that space is three-dimensional. Saying the same thing from a different way, if you want to meet somebody for coffee, you need to give me three numbers to say where to meet them. One way of thinking about that would be latitude and longitude and height above ground. Ordinarily, we're lucky enough to know the height above ground of the people we're going to meet, but you might tell them which of the two cross streets you're going to meet at. So it takes three pieces of information to locate something in the universe. That's what it means when we say that space is three-dimensional. Space is the arena in which things play out. Space is where you locate things, how two things come together, and how things are distributed all throughout the universe. Time, on the other hand, tells you when things happen. So say you're going to meet that friend of yours for coffee, and you give them the three numbers that say where you are going to meet them. That is not enough. You will not successfully meet them if you only give them those three numbers. You need to give them a fourth number, which is when you're going to meet them. So it takes four numbers to specify a unique point in the universe. The three numbers to tell you where you are in space, and the one number to tell you what time it is. You could think about all of these four numbers as being part of one four-dimensional thing called space-time. For a long time, people didn't think that way because there was no point. Space is something that is very clearly different than time. Part of the revolution of relativity, as Einstein understood the universe, is to realize that space and time are in fact two different aspects of the same thing, a single four-dimensional thing that we call space-time. So what we're going to do in this lecture is start with Isaac Newton. Newton was probably without a doubt the greatest physicist who ever lived, and one of the things he did was to put together a very sensible picture of space and time. In Newton's picture of space and time are absolute. They're fixed structures of the universe. They are the stage in which the drama of physics plays itself out. Now, Einstein comes along, and he had collaborators also. He wasn't alone. In 1905, Einstein put the finishing touches on something called special relativity. Special relativity was a replacement for Newton's notions of space and time. Special relativity was the thing that first said that space and time are different aspects of the same four-dimensional thing called space-time. So in special relativity, there was still a fixed structure, but the thing that was fixed was one four-dimensional space-time, not separately the three dimensions of space and the one dimension of time. Then Einstein still thinks, he's not done yet, he tries to incorporate gravity into his theory of special relativity, and he realized that they're incompatible. He eventually throws away special relativity, replaces it with something better, which we call general relativity. General relativity is just as good as special relativity, but it also includes gravity. And the profound difference is that now nothing is fixed. Nothing is given to you ahead of time in general relativity. The very structure of space and time themselves are dynamical. They can change. Space-time has a geometry and a curvature, and it's that curvature that we interpret as gravity. So that was the short version of the story. Let's go slowly through the longer version. Here is a picture of Sir Isaac Newton, as I said, arguably the greatest physicist of all time, also arguably the greatest mathematician of all time. It was Newton who invented calculus, among other things, and among the pieces of physics he invented the fact that when you pass white light through a prism, it separates into colors. He invented the law of gravity that we know and love, the inverse square law. The gravitational force between two objects goes down as they get further away, and as you double the distance, the force of gravity goes down by a factor of 4, the square of the factor of 2 that you double the distance by. So that inverse square law of gravity will play a very crucial role in what is to come, but it is not what we're going to be talking about in this lecture right now. What we care about today, right now, is what Newton said about space and time. So we think that space and time are so immediate and obvious there's almost nothing to say. That's where things happen. Space tells you how to locate things. Time tells you when things happen. What more do you need to know? But one of the great features of the Newtonian revolution in physics was being quantitative, attaching equations to things. It wasn't good enough to just say, well, space is where things happen. You need to have some equations, you need to have some mathematical structure. So Newton did that. Newton told us what it means to say that space is an absolute three-dimensional set of points, and that time is a different, absolute one-dimensional set of points. The basic picture of the Newtonian universe is shown here in this diagram. It's taking the 4 dimensions that you need to slice up the universe and slicing them up into moments of constant time. Sadly, on a 2-dimensional picture, I cannot draw all 4 dimensions of space-time, so the 2-dimensional planes that we've compressed diagonally in the picture are supposed to represent all 3 dimensions of space. So this picture should not be intimidating. It's a fairly straightforward representation of the universe according to Isaac Newton. We know better now, and we'll get to how we know better now, but this is how space-time worked according to Newton. There was space, and there was time. So what you see here is little clocks. Each clock tells a different time located on a different moment of space. So the Newtonian universe is one where space happens over and over again. It happens at different moments in time, and at every moment, objects are going to be located in slightly different places. And so we call that motion through space. Things change as a function of time. And that's how Isaac Newton's universe worked. So the point that I'm emphasizing about Newtonian space-time is that it is fixed and it is absolute. So what does that mean? Those are 2 different words. Fixed means it never changes. There's the structure that space and time are staying there. They don't change into something else. The rate at which time flows does not depend on where you are. There's one fixed thing called the flow of time, and it's the same all throughout the universe. That's what fixed means. Absolute means it's the same for everybody. The rate at which time flows, or the distance between 2 objects, doesn't depend on who you are. It doesn't depend on where you are, on how you're moving through space. It's just a notion. There's a notion of it took 3 seconds between this event and that event. Everyone agrees on the fact that it takes 3 seconds between these 2 events, no matter where they are, no matter how they're looking at it, so long as they take accurate observations. These will change, these notions, once we get to relativity. Absolute, in the Newtonian sense, is opposed to relative. So the absolute fact that a certain object has a certain length is going to turn to a relative fact in relativity. What that means is that the length of an object will depend on who is measuring it. Depends possibly on where they are, certainly on how fast they're moving. Fixed is what we'll get rid of when we go from special relativity to general relativity. In general relativity, space-time is dynamical. It can change, and it can take on different forms, and it will no longer be absolutely fixed. So to understand the change from Isaac Newton's absolute space and time to Albert Einstein's relative notion of space and time, we have to understand how you would go about operationally making sense of Newtonian space-time. In other words, it's one thing for me to say, yes, there are moments of time that are the whole 3-dimensional universe of space, and those 3-dimensional spaces repeat themselves over and over again. But what does that mean? How do you make sense of it? The way you make sense of it is doing something that you see in spy movies all the time. You synchronize your watches. So when I say that there's a moment of time that extends throughout the universe, what that means is I have a clock right here. It says a certain time. And I can set up clocks all throughout space that agree with this clock. So when this clock says it's 3 o'clock, it is 3 o'clock here and everywhere else. These are just a set of words. How do I make them real? What I do is, first, I set clocks throughout all the universe. That's the easy part. We're doing thought experiments here. These are not real experiments. We have a clock sitting at every point in space. But we have to synchronize our clocks. So we take the clock that we have here. We take for granted that we have good clocks. These are clocks that run at the same rate. They are reliable clocks. So we take the clock we have here, we leave it here. But we take another clock and we set it to say the same thing as our first clock. And then that second clock that agrees with the first one, we move throughout the universe. We move this clock, as shown in the picture right here. We move it to all of the other clocks. And when we get to another clock, we align them so they're reading the same time. By that procedure, we synchronize our clocks all throughout the universe. It doesn't matter what the clocks are doing. It doesn't matter how they're moving. It doesn't matter where they are. When we do this, when we take our one clock and we make sure that every other clock all throughout the universe agrees with it, we're done. We've synchronized our watches, as it were, all throughout the universe. That's what Isaac Newton says happens. There's only one rule in Newton's universe, which is that you have to move forward in time. In other words, if it's 3 o'clock here, then when my watch goes 1 hour to the future, I will be at 4 o'clock no matter where I am in the universe, no matter what I've done in the meantime. Then Einstein and his friends came along in the early 20th century and says, actually, it's not like that. We need to replace the absolute notions of space and time that Newton had by relative notions of space and time. In particular, the fundamental insight of Einstein can be summed up in the phrase, time is like space. So what is that supposed to mean? Suppose that you measure the distance between 2 points. You have a path that goes from one place to another. Well, you have to actually go down that path and measure the distance along the path. The distance could be different depending on the path you take. Einstein says that time is like that the rate at which time flows depends on what you do. This is really hard to get through your brains because it's very non-Newtonian. In some sense, even though Newtonian mechanics is a great triumph of the human imagination, it's still quite intuitive. It makes sense to us once we understand it. Relativity is very counterintuitive. Einstein says that the amount of time that you feel elapsing is personal. It's not a fact of the universe, it's a fact of what you do. It can be different for two different observers, even if they start and end at the same point. So let's see how that works. Imagine that you do in Einstein's universe, that is to say in the universe in which we actually live, what you try to do in Newton's universe. You try to synchronize your clocks all throughout space. So you take the clock that you leave here, it's reading a certain time, you take your movable clock and you make them agree, then you send out your movable clock to synchronize all the other clocks all throughout space. You think you've done it, but then you bring your clock back to where it started, and you notice that the two clocks don't say the same time anymore. It's not true that this clock, even though it's a perfectly good clock, clicked at the same rate as it traveled throughout space, synchronizing all the other ones. In fact, it turns out that in special relativity, there is no way to make that happen. You didn't make a mistake. It's just a feature of space and time that when a clock moves around, it measures a different amount of time than a clock that stays still. This seems weird to us because to make the effect obvious, you need to move close to the speed of light. The speed of light is the magical velocity in the theory of relativity at which all of these weird things become obvious. Since we're always in our everyday lives moving slower than the speed of light, we don't notice them. We think it's very strange for someone to say the amount of time that clicks off on my wristwatch depends how I walk, depends on the journey I take through space and time. But once Einstein tells us that time is kind of like space, there's a way of thinking about it that makes perfect sense. So in this picture, we're drawing an analogy between distances and times, because Einstein says that the two things work the same way. You draw two different curves that connect 2 points in space. One curve is a straight line, and one is sort of a curvy thing that goes back and forth. Nobody in the world is surprised at the fact that the length along those two curves is different, even though they begin and end at the same point. Why should they be the same? They move in different ways. So Einstein says time works in the same way. Take 2 points in space-time. take two events, two points where you're both located in space and time. Two people begin at the same point, and they end at the same point, but they take different journeys. One just sits there, not moving, and one zips around. In space, it was the case that the shortest distance between 2 points was a straight line. Any curvy path you went along gave you a longer distance. Einstein says that a very similar thing happens with one interesting twist. Einstein says that the longest time that elapses between two moments is if you just sat there and waited for time to go by you. If you zip off and come back, you will have experienced less time than your friend who stayed behind. The shorter time is the path through space-time that zips around. There had to be some difference because we know that time is not exactly like space, but Einstein is telling us that deep down, space and time work in similar ways. Just like the distance along a path can depend on how you move, the time that elapses on your wristwatches depends on how you move through space-time. So that's the fundamental difference between space-time in Einstein's universe and space-time in Newton's universe. But remember, there was one rule in Newton's universe. You had to move forward in time. That rule gets replaced in special relativity. And in fact, the rule that you have in special relativity is more stringent than the one that had in Newton's universe. In Newton's universe, you could move as fast as you wanted as long as you kept moving forward in time. In Einstein's universe, the speed of light is special. So if there's an event in space-time, and you want to get somewhere else in space-time, you can only plausibly get there if you move slower than the speed of light. So if you imagine drawing a picture of space-time, and you have an event and you imagine all of the light rays that are leaving that event, those light rays represent the ultimate speed limit. They represent the velocity faster than which you cannot travel. So there is no allowed trajectory through space and time that moves faster than the speed of light. Everything you're allowed to do moves up in that diagram. It eats up more time than space, if you like. So that is the fundamental rule in special relativity. Newton's rule is you have to move forward in time. Einstein's rule is you have to move slower than the speed of light. That set of things, faster than which you cannot go, is called a light cone. The set of all points connected to your original event by things moving at the speed of light. So the only thing you need to remember is, whatever the speed of light is, where you are in the universe, you need to move more slowly than that. That is the fundamental rule. So this was a replacement, as we mentioned, for Newton's concept of space and time. Newton was the greatest physicist who had ever lived. He invented not only this notion of space and time, but also the theory of gravity and many other things. So Einstein knew that if he's going to replace Newtonian space and time, he would have to reproduce the other successes that Newton had. Newton had a very good theory of how gravity worked. He was able to predict how planets moved around the sun or how the moon moved around the earth. This theory of Newton's was verified to high accuracy over and over again by experiments. And here comes Einstein saying it's not right. So clearly you have to reconcile the new theory of space-time, special relativity, with what Newton thought gravity was. Gravity was the inverse square law. The force due to gravity is proportional to the mass of the thing that is pulling you, and inversely proportional to the distance squared between the objects. So after inventing special relativity in 1905, Einstein devoted himself to this task of trying to figure out how to reconcile gravity with his new notion of space-time. It took him 10 years to do it, and the way he ultimately did it was to realize just you needed to throw away what Newton had told you about gravity. The way that gravity was going to work in relativity is just very different than it works in Newtonian mechanics. So here's a picture of Einstein. You've all seen pictures of Einstein before, but usually when you see pictures of Einstein, he's in his older ages where he has let himself go a little bit. He had the hair going up like that, and he was wearing a sweatshirt, and he wore the same sweatshirt for days and days. This is a picture from 1912 when Einstein was young, a sharp-dressed man, and somebody was combing his hair, and he was thinking about the nature of space and time and how to make it compatible with gravity. Ultimately, he hit on a thought experiment that provided the key to understanding how gravity would work in the context of relativity. And the thought experiment actually traces itself back to Galileo. Galileo, the famous Italian physicist who lived just before Newton, who really invented a lot of the framework that Newton made sharp and quantitative and attached equations to. Galileo was one of the best physicists of all time. One of the many, many things that he did was to understand that gravity is universal. The famous experiment that he may or may not have done, probably not, but it's a nice visual image, is to drop objects off of the Leaning Tower of Pisa and notice that no matter what the objects are made of, no matter what the mass of the objects is, they always fall at the same rate. In other words, gravity as a force has a very strange characteristic, that everything responds to it in the same way. So that's different, for example, than the force of electricity. The electromagnetic force has the property that there are things called positive charges and things called negative charges. They move in different ways, in opposite directions, in an electric field. But gravity, everything moves the same way. Gravity has this feature of universality. Everything responds to it identically. So Einstein, because he's smarter than you or me, realized that this was the key to understanding how gravity works, the fact that it works the same on everything. What that meant is that gravity is undetectable. That's a bit of a surprise to say that gravity is undetectable. It seems kind of obvious that if I let something fall, I see the force of gravity at work. But what Einstein says was, imagine that you're in a box. You can't see outside. Someone asks you the question, is there gravity in that box, in that room? Well, you can drop things, you can see them fall, and you go, yes, I have seen gravity. But Einstein says you might be very far away from any gravitational field. It might be that you're in a rocket, that you're being accelerated at a tremendous rate through interstellar space where there's no gravity around. In that rocket, if you drop things, they will fall in exactly the same way that they would fall if there were gravity. This is not true for electricity. You can detect an electric field because you drop a positive particle and a negative particle. They move in different ways. But because everything moves the same way under the influence of gravity, you can never be sure, if you're in a small region of space-time in a tiny little box, that there is any gravity. So again, to you and me, we say, well, that's interesting. To Einstein, he says, that's the key. If everything responds to gravity in the same way, then gravity is not a force at all. Gravity is a feature of space-time itself. In fact, the feature it is the curvature of space-time. Einstein's most brilliant insight was to say that space-time has a geometry. And in 1915, he came up with general relativity, which was to describe how the geometry of space-time, how the curvature of space and time itself, manifests itself as what you and I observe as gravity. So according to Einstein, we have a picture something like this, although this is a somewhat colorful conception of what is going on. We have the sun that is warping the space around it. The usual analogy that is used here that is pretty good is that you put a bowling ball in a rubber sheet, it distorts the shape of the rubber sheet around it. And a marble that you rolled by that bowling ball would be deflected by the curvature of the rubber sheet. What Einstein is saying is that that is what is happening in space-time. That is what gravity really is. The gravitational force that we attach to the sun is really the warping of the geometry of space near the sun. What the Earth is doing is the Earth is just doing its best to move in a straight line. But there are no straight lines because the geometry itself is curved. So what we see the Earth do is to orbit the sun. The orbiting of the Earth around the sun is just the Earth's response to the geometry of space and time. This was Einstein's brilliant idea. Now again, it's not enough to just say words like that. You need to make it quantitative. So Einstein has an equation known as Einstein's equation. Einstein's equation is not E equals mc squared. That is a very good equation, and it is Einstein's. It's very famous, and we'll talk about that more later. But what is known to physicists as Einstein's equation is the equation for gravity. And I'm going to show it to you here, again, not because we're going to understand this equation in any great detail, but it's nice to see just what it looks like. You should get an appreciation for the art and the poetry that are these physicists' equation. This is Einstein's equation, and what it is a left-hand side and a right-hand side. So that part is easy. The left-hand side is describing the way in which space-time is curved. It's a set of numbers. In fact, it's a 4x4 matrix, a little array of 16 numbers, and the values of those numbers are telling you by how much space-time is curved. If space-time is flat, if it's like this tabletop, if there's no geometry, all those numbers will be 0. On the right-hand side, you have stuff. So you have 8 pi and g. These are just constants of nature. They're just fixed numbers. And then you have the energy and momentum of the stuff in the universe. Anything that is in the universe comes along with energy, comes along with some substance and some heat and some pressure and things like that. And what Einstein is telling you in very specific equations is that all of those things contribute to the curvature of space-time. What Newton would have told you is that what makes gravity is mass. What Einstein is telling you is that what makes gravity is everything. Every form of energy, which includes mass, but also includes heat and pressure and temperature and stress, these all contribute to gravity in some way. So this equation, Einstein's equation, is the one that should be famous. It's a little bit more intimidating than E equals mc squared, a little bit less immediately relevant to our lives, but it's a tremendous accomplishment to conceptualize gravity as a feature of space-time itself, as a feature of the curvature of space and time. So you're allowed to ask, who cares? Why should it matter that I use the words gravity is the curvature of space and time rather than gravity is a force stretching through space and time? Is there any difference between these two sets of ideas? Well, there are differences, and the differences are going to make a big difference to us in our quest to understand cosmology, dark matter, and dark energy. The first implication of the claim that gravity is the curvature of space-time is that universality, the fact that everything responds to gravity in the same way, implies as its converse that everything creates gravity in the same way. There's a universal coupling between the curvature of space and time and the stuff in the universe. In other words, you can't hide from gravity. If there is stuff in the universe, if it has mass and energy, if it exists in any substantial physical way, it will give rise to a gravitational field. So Einstein is giving us a surefire technique for detecting absolutely everything in the universe. There is nothing that can hide from us as long as we can detect gravitational fields throughout the cosmos. You can't hide from gravity, so you can go the other way. By detecting gravity, you can infer that there must be stuff. If you see a gravitational field pointing in some direction, there must be some stuff there causing that gravitational field, even if you don't see the stuff. This will be the technique that we use to infer the existence of dark matter and dark energy. Dark matter, we will say, must be there because we will see stuff being pulled in some direction where there's not enough ordinary stuff to explain it. Dark energy has a more subtle effect. It makes the universe accelerate. And we'll talk about how the acceleration of the universe is a manifestation of the curvature of space-time in the way that would be caused by dark energy. The second implication of the motto that gravity is the curvature of space-time is that space-time is dynamical. Space-time can change as a function of time. It need not be the same in the past as in the future. So it gives us a changed viewpoint on how we would think about the fact that galaxies, for example, are moving away from us. Hubble said that we have a velocity to galaxies, and the velocity is larger if the galaxies are further away. The same phenomenon makes sense according to Einstein, but we attach slightly different words to it, which is why when I'm being careful, I refer to the apparent velocity of distant galaxies, not the actual velocity. In the real, careful way of understanding things, a la Einstein, the galaxies aren't moving. The galaxies are sitting there, located in space, and what's happening is space is expanding. Space-time itself is dynamical, it can change, and what is happening is not that the galaxies have a velocity through space, but that the space in between the galaxies is growing, it's stretching, it's getting bigger. More and more space is coming into existence. This is a way of thinking about things that Einstein gives us that allows us to ask questions that wouldn't have made sense to Isaac Newton. We can say, for example, where did space and time come from? What happened at the beginning? Did space and time get created? Was there something before what we now think of as the Big Bang? To Newton, with an absolute fixed space-time, this kind of question doesn't really make sense. You don't ask where space-time came from for Isaac Newton. It was always there. With general relativity, saying that space and time are dynamical and can change, you're at least allowed to ask the question, why are they here? How do they come into existence? You will not be surprised to hear that we don't yet know the answers to these questions, but we're hopeful that our understanding of dark matter and dark energy will be part of the clues that help us answer them eventually.